So one of the funny elements of reflection is reflection through spherical surfaces. The funny figure or the funny image which we come across while moving past in a funny mirror in a circus is because of the different spherical mirrors arranged in front of us. So we'll now figure out and quantify with mathematical expression corresponding to reflection through spherical surfaces. In this, we will study about the mirror formula and the magnification and its applications. So let's see what's in store for us. So now the diagrams, that is the ray diagrams corresponding to the object placed at a different position from a concave mirror. So I can classify the position from the concave mirror basically in three cases. One, when the object is kept between the center of curvature and the focus, when the object is kept between the focus and the pole of the mirror, and when the object is kept beyond the center of curvature over here. So corresponding to these, I have images over here, images over here, and images over here. Sorry, this is the object, so the image seems to be over here. Now, if you noted, these are real images. That is, the image, or let's say the point, is an actual point from where the light is appearing to be coming from. So the real image is an actual intersection of the light rays. This point is not a luminous source. This point is a point where the light rays cross path. So for an eye, it actually appears that this point is a source. Hence, the real image. If you look at over here, the light rays which are extrapolated are like this. So there is no actual origin of this point, but our eye actually perceives that it's coming from this particular point. That is a virtual point. So this is denoted as virtual image because it doesn't really exist. Our eye perceives that it is, or it is real in nature. So one type of image is virtual image, the other type of the image is the real image. Moving on. Now we will look into the different types of images which will be formed corresponding to convex mirrors. Now please keep in mind that all the rules which we have studied for dealing with the images corresponding to concave mirror, the same rule kind of applies in case of convex mirror as well. That is, the light passing through the focus after reflection becomes parallel. Light parallel to the principal axis after reflection passes through the focus. Light passing through the center of curvature after reflection retraces its path. So these three features are constant in all sorts of mirrors, whether it's a plane mirror or whether it's a spherical mirror. So the same points, these 1, 2 and 3, these 3 points are being depicted in this diagram. And correspondingly, in the form of sentences, it's been written like this. That is initially parallel to the principal axis, and it appears to originate from the focal point after the reflection from the mirror. It appears, please mark this word, it appears. It's not in reality, but it seems it's exists over there. Same goes for the other part, that is a ray heads towards F, emerging parallel to the principal axis after reflection. The third one, this ray travels towards the center of curvature. As a result, the ray strikes the mirror perpendicularly and reflects back. In this case as well, the light is trying to reach center of curvature, which is on the other side of the reflecting surface. So it seems that the light is coming from that point and it's reflected in the same direction. So it retraces its path. So whatever we actually observe in reality, that is in context of concave mirror, in convex mirror, it appears that it's happening the same way. It doesn't, but it appears. They both have the same consequence, but in convex, it doesn't really happen. In concave, it actually happens. That's the difference between the images formed by concave mirror and convex mirror. Now, one of the most important aspect of mirrors, that is reflection, let's say for the whole of the reflection is the mirror equation. Now the mirror equation is basically a mathematical expression which connects three parameters: the image distance, the object distance, and the focal length of the mirror. That is, I have the cause and effect. Cause is an object, effect is an image. So if I place an object in the front of a mirror, I will end up getting an image. So the cause and the effect, they are related via the parameter of the reflecting surface, that is the focal length. So the mirror equation for, let's say these are the parameters. First of all, stands for the focal length, D0 stands for the object distance, Di stands for the image distance, M stands for the magnification. Magnification in the nutshell is height of the image divided by the height of the object. That's the magnification. Now, these are the typical diagrams corresponding to the reflection for concave mirror at different positions. Now, the mirror equation actually comes out to be this: 1 by D0 plus 1 by Di equals to 1 by F. 1 by, that is the reciprocal of the object distance, plus the reciprocal of the image distance is equal to the reciprocal of the focal length. And the magnification is given as this. That is, I will write it again to explain you in a better sense. That is, M is equal to Hi by H0 and is also equals to Di by D0. Is the same, that is the magnification, the definition is image height divided by the object height. Now, if you work out the geometrics, let's say in the previous figure, if I try to work out the geometry of this setup, I will end up finding this relation, that is Hi by H0 is equal to minus Di by D0. I will end up finding this relation if I apply similar triangles by selecting a correct pair of triangles. If I am able to select that, then I will end up having this relation. So it's just a mathematical relation which kinds of is very useful in a situation where we don't have any idea, or let's say we have a limitation to measure the object or the image height. In that case, we work it out using the image and the object distance. Now, again, let's say to properly apply the mirror equation, we need to keep in mind the sign convention. That is, the focal length is negative for the concave mirror, right? So the concave mirror is like this. The direction is in this direction. This is a sign convention. The light is moving in this direction. Any distance measured in this direction is positive. Any distance measured in opposite direction, that is direction opposite to the propagation of light, that's negative. So this one is negative, this one is positive. This one is positive, this one is negative. So if I consider any general mirror, let's say I consider my concave mirror, the focal length is over here. So this is the focal length. So focal length is negative for the concave mirror. And focal length for the convex mirror will obviously be over here. So the focal length for the convex mirror is positive. Similarly, you can find out the convention regarding the object distance and the image distance. That is, for the object distance, it's negative for the real object and it's positive for the virtual object. That is, virtual being it's lying on the other side of the reflecting surface. Similarly, for image distance and magnifications, these are the simple trivial things which is given in this particular slide. So please go through and just make sure that every base, or let's say every concept regarding the mirror equation is covered. Because the students end up making mistakes through sign convention. That is, if I ask you to evaluate this 1 by D0 by 1 by Di is equal to 1 by F, and if I end up giving you that the focal length of my concave mirror is 20 centimeter, so what basically the students do is they straight away evaluate F is equal to 20 centimeter over here, which is actually not correct. So the correct answer should be, or it's given that it's a concave mirror, it means F in reality is minus 20 centimeter.
Please do keep this in mind.
Now let's check out a video, or let's say a simulation based on the reflection of a light. So majorly this simulation is for you guys to get accustomed to the coming simulations regarding refraction. So all of you are very comfortable as far as reflection is concerned. So this was just a dry run for you to make sure that you are totally accustomed to this simulation once we actually start our dealing corresponding to refraction. So this is kind of very simple reflection. So this is a medium. So if I play around with this, that is moving, let's say increasing the angle with the normal, decreasing the angle with the normal. Correspondingly, I have different situation. Over here I have the index of refraction n for the material. That is, I'm changing the refractive index, and this is what happens. You can clearly see that is the medium in which the light is actually traveling. If I play along, you see it's moving away from the normal. So I don't intend to tell you about the refraction right now. I'm just making you comfortable with this particular simulation. Again, with this material, that is right now, I'm decreasing the refractive index of this medium which you are seeing over here. Let's put it over here. Fine. So again, angle of reflection is equal to angle of incidence, which we can easily see over here. I have a tool over here to make sure that we end up getting that. So I've put it exactly at 0 degree. This is normal and this is 0 degrees. So let's check out for angle of incidence 30 degrees. So you can just see that this is 30 degree, this is also 30 degrees. Then our famous 45 degrees. Again, for 45 degrees I end up getting to be 45 degrees. If this is 60, I end up getting 60, 75, 75. So this is just reflection, which is kind of easy. Everyone knows about it. So make sure you are very accustomed with the different things which we have over here. So again, one other cool thing which I can show you about is I can represent light to be as a wave. So we have discussed in the introduction part of what light is. So here I can show you light as a wave as well, and light as a ray. For geometrical purposes, I kind of use light to be as a ray. For wave optics purpose, which you will learn in the next series of video lectures of wave optics, so this is wave. You can represent light to be as a wave. So we'll check out more about these interfaces, these simulation in later videos as well. So stay tuned for the lectures corresponding or videos corresponding to refraction, and again more coming up from this end.
Now let's try out a problem based on the mirror equation. Let's say I have a concave mirror. So given that I have a concave mirror, and it's just given that I have a concave mirror and there is an object, and I have no idea whatsoever how my concave mirror is, where is it placed, where the object is with respect to the concave mirror, no idea whatsoever. And the only set of information which is given to me is for 2 points A and B, I have same magnification, or so as to put it, same height of the object. That is, in both the cases, A and B are 2 points where I have kept the same object, that is height of the same object at A and B, and I end up getting an image corresponding to it has same height. That is, whatever be the height of the image corresponding to object placed at point A, when I place the same object at point B, I am getting the image of exactly the same height when I put my object at point A. So these are the 2 points. If I keep my objects over at point A and B, I end up getting the images of same height. So same height doesn't mean I have a same magnification. Please keep this in mind. Okay, so basically same height doesn't mean I have a same magnification. That's the key to the problem. Now the given information is RA position from the pole and RB the position from the pole. We need to find out the focal length. This is what we need to find out, the focal length of the concave mirror. Now I know that the magnification cannot be equal. If the magnification is exactly equal, then according to the magnification it's minus di by d naught. So if the magnification is equal, I will end up getting the image at the same point. So basically A is equal to B, but it's specifically given that A and B are not the same point. So it means the magnification at A is exactly opposite to the magnification at point B. So using this condition, we have to find out the focal length. Now we know that the magnification at any particular point is given to be minus V by U. We also know that V is equal to, that is 1 by V is equal to 1 by F minus 1 by U, or V is equal to UF U minus F multiplied by 1 by U ends up giving me F minus F U minus F. This is my magnification at point A, which is also equal to at minus of magnification at point B. Now the information that is RA and RB are given. So if I substitute the value of RA over here, I'll end up getting MA. If I substitute the value of RB over here, I will end up getting the value of the magnification at point B. Using these two, we will find that the focal length is equal to RA plus RB by 2. That is, if I move my object from, let's say I pick up any particular point and then move the object from one point to the other point, and the relation between the 2 points is such that the images at both the points are having the same height, then the focal length of that particular concave mirror is simply the average of those two distances.
While going through the lecture, if you face any doubt, you can post your doubt for free at askIITians.com. In order to do so, you first need to navigate to the askIITians.com. Then, while going to that link, you can use discussion board link, which is over here. Clicking on this particular discussion board link, it will take you to a page where under the head of Ask the Experts, you can post your doubt under various categories. And the team of Ask IITians Expert will get back to you between 24 to 48 hours. So we studied about convex mirrors, concave mirror, magnification, the different sign conventions associated with the spherical mirrors, and also the application which concave and convex mirror holds in our day-to-day life. So now that we are completely done with the reflection part, both from plane surfaces and spherical surfaces, now we'll shift our attention to the next big thing associated with light. So let's see what's that.